Hi everyone, today we will analyze the structure of crystalline solids. So what the crystalline solid is? If you look at here, this red dot is for silicon and the blue one is for oxygen. If you see, it's arranged in a kind of a pattern. So if I know this pattern, this pattern over here represents this total structure of the material. So if you just copy and paste this single pattern, you get the total material structure. But if you look at it underneath over here, it still is made up from silicon and oxygen, but it's not arranged in proper manner. So it is not in order. This one has different shape and another one has another kind of shape. So because this kind of materials, non-crystalline materials, or in another name, amorphous materials. So how do we get this kind of non-crystalline materials? We have two kinds of situations. The first, the material itself has a complex structure, and the second one is you get crystalline material like this, and if you heat it and then cool it very rapidly. Here rapid stands for very fast. So if you heat silicon oxide and cool it very fast, it may get non-crystalline structure because this atom will not have enough time to get its original position. Let's say it should have been here, but it couldn't because it didn't have time. It did cool, its energy decreased, so it doesn't have energy to move from here to here. And at the same manner, so it should have this kind of shape to be perfect hexagonal, but this atom is stuck here instead of here. This one is stuck here instead of here. So I have unordered pattern because of fast cooling. So what kind of materials could be crystalline? Metals, most of the ceramics, and some polymers may be crystalline materials. So, and what was crystalline materials? The atoms packs in periodic, in a kind of a pattern manner. Let's continue. So here you see two kinds of atomic arrangements. You can see the difference, how this is stacked together. See here I have less empty space. On the other hand, here I have more empty space. Actually, this will affect its mechanical properties of these two materials. So how metals, I didn't say metals because we will mainly analyze crystal structures in metals. So imagine atoms is arranged in this way, like this over here, and if we are stacking another layers to it, so we are adding layers onto it. So I will have second layer, a third layer, and the fourth layer above it. And the same thing will happen here. I may have a second layer just on top of it, or I may have a second layer of atoms. So this atom will sit here, another one will sit here. So different kind of arrangements will give us different kind of materials, different kind of crystal structures and properties. And we will analyze this kind of properties. And we will analyze crystal structures in metals as I have mentioned before. We will analyze 4 this kind of structures, which usually found in metals. We have others, but we will not deal with them. So metals are usually packed densely. Here, dense, if I write this word, maybe it will be similar. It will resemble something for you. It comes from the density. It means it will have higher weight. It will be difficult, let's say, to lift. So metals has higher density because they are densely packed. So why they have dense packing? The first one, In metal structures, usually we have one kind of element, and that means one radius. So imagine I have some metallic element and I am packing it. Because all have the same radius, we will be able to pack them efficiently. Now imagine another kind of scenario where I have two elements, one red ones, let's say, and another blue element which has different radius, so smaller radius. Let's get another red one again. So I have now here two kind of elements. This will have radius 1, this will be radius 2. So because here I have two different radiuses, when I pack them, I have this empty spaces, more empty spaces compared with this one because of different radiuses. So if I have more than one element, less dense packing. If I have one kind of element, more dense packing. And metals has this kind of structures. The second one, why metals has dense packing? Because metallic bonding is not directional. The metals are bonded with metallic bonding. And what was metallic bonding? As a reminder, let's separate them a little bit. So we have iron cores, which is positive, over here, and we have free valence electrons in large values. So these electrons acts as a glue to hold these two positive cores together, so they don't repel each other because this negative sign acts as a glue. And metallic bonding is not directional, so it's this electron and cores are free to assume a position they like. Unlike covalent bonding. So in covalent bonding, it was directional. That's why covalent bonded materials takes more volume because for example, let's say this I have these two more different elements. This element has to be bonded to this small red one, especially at this position. The position is important over here, but here it's not important. That's why I can pack them efficiently closer to each other. The third one, nearest neighborhood distances tend to be small in order to lower bond energy. If two elements is close to each other, like here, they will spend less energy. That's why, in order to spend less energy, these elements tend to get close to each other. And if they are close to each other, we have dense packing. So that's our reasons for dense packing 1, 2, and 3. So let's move on to analyze these crystal structures. For metals, it says 3, but as I mentioned, we will analyze 4 such structures. The first one is simple cubic structure. So we have 8 atoms arranged like a cube. These atoms touch each other. In order to make it easy to see, we have drawn these atoms smaller like this, but actually these two are touching each other. So what you should know first, how does this look like? The polonium element is the only element which was discovered with such this structure, with simple cubic structure. If you pay attention here, it says coordination number equals to 6. What is coordination number? Let's say pick any atom. I will pick this red one over here because it will be easy to see. So coordination number is how many atoms touch this single atom. And what is this value? Let's calculate. This is 1. We'll touch this one. Second, 2, 3, 4, 5, 6 other atoms touches this one. So coordination number is 6. We could pick any other atom. It doesn't matter. The number will be the same. Let's move on. Just pay attention to this animation. What we have here, if we cut atom parts which is outside of the unit cell, what do we have? We get the outside part gone. You see the picture. And first, let me mention, I have mentioned unit cell. What the unit cell is? Unit cell is the smallest pattern. Let's say for this one, let's draw a cube. This is a unit cell. And that means that if you know this pattern, you know the total structure of the material. Just we have infinite amount of these cubes arranged in all directions, and that's the structure of polonium element. This is called unit cell. So if we get rid of atoms which lies outside of this cube of this unit cell, what we have, we cut these outside parts and the part we needed. So if you look at here, we cut out the excess, and if we sum these atoms together, so what we will see, we have one atom per unit cell. We will see in shortly why do we need to do this procedure. So we cut the excess part outside unit cell and sum this, so we get value 1. That means in this simple cubic structure, we have one atom per unit cell. So let's continue. Atomic packing factor. What's atomic packing factor? It shows how full this cube is. It's kind of a fullness ratio. In order to calculate it, we need the volume of atoms in unit cell divided by volume of unit cell itself. So what do we have? If you see, we have atom here and others. But if you see this part over here, it is empty. So we have something full inside and something empty, and we need to find how full is this. That's why I will find the volume of this parts and divide it by volume of cube. So what it will be, how many atoms did we have? We calculated that it was one atom. So atomic packing factor equals to one atom multiplied by, here we are assuming that this atom is a hard sphere, and the volume of sphere equals to 4 over 3 PR cube over. So this part is volume of atoms over volume of cube. If this side is A, the volume of the cube will be A cube. Now we can make it simpler by creating relationship between the radius and the side. And if you see, this is one radius and two radius, and this equals to A. So 2R equals to A, and we can replace it. So it will be 4 over 3 multiplied by P, the P R cube over 2R cube. R cubes will be gone, and if you simplify it further, we will get value 0.52. That means this simple cubic structure is 52% full, and the rest is empty. Let's move on. The second structure is body-centered cubic structure. If you see this infinite amount of atoms over here, we just cut down this small part, that means that this unit cell represents the total structure. If you just copy and paste and you get all of it. So let's take it out and analyze. So we have this kind of structure, 8 atoms at the corners and 1 at the center. If we cut atomic part which lies outside of cube, we get this structure. So how many atoms per unit cell do we have? So this will be 1, and it is total inside. This corner atom will be 1 over 8 part of the total atom, and we have 8 corners in total. 1, 2, 3, 4, 5, 6, 7, and 8 is at the behind. So multiplied by 8 and plus this 1 over here, it will be 2 atoms per unit cell in total, and I will use this 2 to calculate atomic packing factor in the next slide. So here we see that chromium, tungsten, and iron has BCC crystal structure and others. So what's coordination number? Again, coordination number, amount of neighbor atoms that touch single atom. So I will choose this one, this atom at the center, because it's easy to see all those 8 corner atoms touches this one. The coordination number is 8. Coordination number for this atom or for this atom is 8 also, because this corner atom will be center atom of another unit cell, because we have this infinite amount of cubes over there. Let's continue. So atomic packing factor for BCC. Our equation was atomic packing factor equals volume of atoms. So I have 2 atoms which we did calculate in previous slide, multiplied by 4 over 3 PR cube over. So over A cube. So A is the side of the cube. Now we will create a relationship between radius and the side A. Let's see. Here you see that these 2 over here does not touch each other. So but I need to create some relationship. We see this corner atom touches the one at the center, and center atom touches this one at the far back corner. So it is a diagonal. If I know that this is side A and this is A, I can draw a triangle over here. So it will be A square root of 2 by using Pythagorean theorem. This is A, so A square root 2. This will be A square root of 3. Let's take this triangle out. I mean this triangle. Let's take this triangle outside over here. Side A, side square root 2A, and this side square root 3A. And these atoms over here, this is corner atom, this is at center atom, and this one is this corner atom over here. So how many radius do I have? R, 2R, and 1R. So that means 4 radius equals A under square root of 3, and A is equal to 4R over square root of 3. So we can just make replacement PR cube over 4R over this. So R cubes will be gone, and if you just simplify it, we get 0.68 atomic packing factor for BCC. If it was difficult for you to understand how to calculate atoms per unit cell, you can watch this animation. So it cuts the excess part which is outside of unit cell and sums them. So as you see, we have 2 atoms inside unit cell, and we use just 2 over here. The free center cubic structure. This structure, this cube, over here represents the total structure for face-centered cubic structured elements. Let's analyze it in details. So as you see, we have 8 corner atoms, and at each face we have 1 atom. So 6 atoms at the faces, 8 at the corners. These two doesn't touch each other, but it touches in this face diagonal. Let's see. Aluminium, copper, gold, lead, nickel, and others has FCC crystal structures. Let's move on to calculate coordination number and this atoms per unit cell. So here let's first short in total. That is FCC crystal structure by layers. So I'm adding layer by layer. This blue one is corner atoms and the red one is a face atom. Now I will add another layer. It is a second layer. All these 4 red ones will be face atoms. Now the last layer, blue ones is a corner atoms, red one is a face atom. I picked it dark red because I want to differentiate it because I will calculate amount of nearby atoms for this one. So coordination, I will calculate coordination number related to this. So in order to do this, so how many atoms touch this one until now? We just move back. These 4 red atoms touch this one. So I have 4. Actually, it's writing it 1, 2, 3, 4. And this 4 also touch this one. 5, 6, 7, 8. But it's not over because we have infinite amount of layers. As you see, blue layer, this red layer, blue layer. Let me add another layer in front of it. Because it is infinity, I will have infinite amount of layers. So in front of that cube, I will have another cube. And these atoms will touch that dark red one. So it will be 9, 10, 11, and 12. So in total, 12 it will be coordination number for FCC crystal structure. I hope it was clear for you. Let me do this one. This last blue one will not touch dark red one. It's clear. So if you just separate others, this 4, and this blue force touches single dark red atom, and we can calculate this value for any other atom, but I just picked this one to make things easy to see. The our coordination number was 12. Let's continue to calculate atoms per unit cell. How many atoms do we have in FCC unit cell? Let's watch it again. Actually, pick out the excess part outside unit cell, and that's it. And sum all of them will have 4 atoms per unit cell. Just move to the previous slide. So each corner atom here is 1/8 part, and I have 8 corners plus this one will be half, and I have 6 faces. So in total it will be 1 plus 3 equals to 4 atoms per unit cell, and we will use this value to calculate atomic packing factor. Let's see. Atomic packing factor for FCC. Our equation was equal to, so volume of atoms, I had 4 atoms in unit cell, and the volume PR cube over, if this side is A, it will be A cube. Now I have to create a relationship between radius and this side A. If you see, These phase atoms touch each other in this manner. So if this side is A, this side is A, this will be square root 2A. Imagine this kind of triangle, A, it is 90 degrees, and it will be this. And atoms touch in this manner. So I have radius, 2 radius, and 1 radius over here. So 4 radius equals to this, and A will be equal to this. So we can just make replacement. PR cube over, so R cubes will be gone if you just replace P with 0.14 and simplify, we will get 0.74 atomic packing factor, which is one of the highest values inside crystal structures. That means an element which has a crystal structure will be heavier because it's densely packed. It is full. Actually, if you know, let's actually keep it like this. So let's move to next slide. So until now, we have discussed 3 cubic structures: simple cubic, face-centered cubic, and body-centered cubic. The first one is hexagonal close-packed structure. In short, I will use HCP. If you see this pattern over here, hexagon, and at the center of hexagon, I have another atom. Let's take it out and analyze. So that's what we have here. Hexagon, 6 atoms at the corners, 1 at the middle, the same layer underneath, and at the center, 3 atoms, which is total inside of that hexagon. So I have layer A, layer B, and layer A. Underneath it continues B, A, B, A. We just choose this 3 is enough to represent it. So let's try to calculate, actually first, what we have here, magnesium, titanium, and zinc has hexagonal close-packed structure. Let's calculate how many, actually, let's see which one comes next. Let's calculate what's coordination number for hexagonal close-packed structure. So how many nearby atoms a single atom has. Let's see. You see, I have tried to draw here 6 hexagon, 3 underneath, 1, 2, 3 here, and 1, 2, 3 here, 6 in total. And if you see, this red atom is actually, sorry, here I will show you how many atoms per unit cell we have. I will keep coordination number for the next slide. Just wait for it. So this red atom is shared by 6 hexagons. So this one is a coordinate atom of another of 6 hexagons in total. So this hexagon over here will have 1/6 part of it. So each one has 1/6, and this one also. So in total, so 1 atom. So this atom's 1/6 part is inside this hexagon. I have 6 coordinate atoms like this. So it will be 1/6 multiplied by 6 plus this atom over here is shared by 2 hexagons. So this black and red shares this atom. So it will be half over here and half over here plus half. This kind of pattern is repeated underneath. I have exactly the same pattern over here. So that's why I will just multiply it by 2 and plus. At the center, if you remember, I had 3 atoms, which was totally inside. So at 3, it will be 2 plus 1 plus 3, 6 atoms per unit cell. That means if you just get rid of this part, which is outside, and sum all atoms, which is total inside of hexagon, we will have 6 atoms per unit cell. So let's continue this time to find coordination number. I will represent it by layers. That's our first layer of hexagon, second layer, and third layer. I differentiated this like dark blue because I will try to calculate coordination number for this one. And just to make it easy to see, I chose this one. Until so far, you see that this 3 yellow will touch this one, this 6 around will touch it, but I have infinite amount of layers. So this is layer A, layer B, A, and I will have another layer above it. So this 3. It's clear that this outside will not touch this dark blue one. So let's get rid of it. If you just separate it a little bit, it will be easy to see it. I have 3 over here that touches this atom, 6 around it, 1, 2, 3, 4, 5, 6, and 3 underneath. Underneath, in total, 12. The coordination number for HCP is 12. So, and atomic packing factor was 0.74, which was same with FCC, but I will not show you how to calculate APF for this one because it will take a little bit more geometry. You can search it online. So just remember the value, 0.74. We have captured main crystal structures for metals. I will give you a summary of it. Actually, just wait for it. So what we have here, polymorphism. So far I have mentioned that certain elements have certain crystal structures. For example, titanium, if I remember correctly, was HCP, aluminium was FCC, and etc. But some elements has more than one crystal structure, such as if you look at your iron over here. So iron, if it is under 912 degrees Celsius, iron will be BCC. So iron has BCC crystal structure. If you heat iron above this temperature, it will transform to FCC. And if you increase temperature further, it will return to BCC again. So one element has more than one crystal structure, and it's called polymorphism. So if you see BCC iron is called alpha iron, FCC iron is called gamma iron. In further chapters, we will see this in details. So here, if you see, we have carbon, diamond, and graphite, which has the same chemical composition made of carbon. But as you see, diamond is very hard, graphite is very brittle. And what was brittle? Let me give you some vocabulary. Brittle, let's say, it's easy to break it. So why do these have different characteristics? Because they have different crystal structures. That's it. So carbon, it has also got polymorphism property. Before I will not move to this slide in this video, but I want you to capture what did we learn so far. Let me find some empty space. We have learned crystal structures, simple cubic, FCC, BCC, and the last one, HCP. What are you required to do is you have to learn how does this looks like. What do they look like? What their coordination number is? What the APF is, and atoms per unit cell. What this value is? You have to learn this. It's kind of a summary. And that's it for this video. I hope I made things clear. So, thanks.